Hello everyone, I welcome you all to another class of biomedical ultrasound course, and in today's class we will be talking about the characterization of materials, and I am Simranjeet Singh, NPDA fellow at IISc Bangalore. Coming to the very basic question, we will initially talk about why do we need characterization, and before even talking about why do we need characterization, let's talk about materials. Now let's come to the very generic question, like what are materials. Now if you look around yourself, the chair in which you are sitting, or the table on which you are keeping your laptop, or even in the screen that you are viewing me, so everything is made up of some kind of materials, and materials are made up of matter. Now matter has a very generic definition. Anything that occupies space and have mass is called matter. Now every matter in the universe is made up of molecules which are bonded together by some kind of bonds, and because these bonds are unique to that particular material, so they will have a specific or generic properties or some characteristics like color, shape and sizes, etc. So let's talk about the very basic examples. Like coming to the very basic examples of properties of materials, let's talk about. So supposingly we have this object, so supposingly we have this pen. So what is the first thing that you will see or about this pen? So you will probably say that the first thing I will notice about the pen is about its color. So the color that you are seeing is the pinkish red. So this is because it is reflecting the pink color and it is absorbing all the other wavelengths. So that we will say is its optical property. Now talking about another property, let's talk about the thermal one. So if I heat this pen from this end, it will eventually melt because it is made up of plastic, but I won't feel the heat in the other end because it is a bad conductor of heat. So this we already know because of the property of plastic. And supposingly if I replace this plastic pen with a metallic pen, so metallic pen, if I heat from here, I will instantly feel the heat at the other end because metals are a good conductor of heat. And similarly, if we go to the electrical properties, so if I make a circuit using a bulb and the battery and I place this pen in between them and I complete the circuit, I will see that the bulb will not glow because our pen, which is made up of plastic, is a bad conductor of electricity. And if I replace this with a metal or some other form of metal, I will see that it will conduct electricity because the metals that we have are a good conductor of electricity, because these are the electrical properties of the plastic pen and the metal that I am talking about. Similarly, if I talk about some of the very basic generic mechanical property, so if I have to bend this pen will eventually break. And if this is made up of metal, so metal have a property that it can be drawn into wires. So if I bend a metal, it will easily bend, but if I try to bend this pen, it will eventually break. So these are the properties of the metals and the plastic that I am talking about. Similarly, let's talk about some other properties. So if I have this pen and I have dipped it in water for around 30 minutes, 40 minutes or even a day, what do you think will happen? Yeah, nothing will happen to this pen because right, it's made up of plastic. Now if I have a pinch of salt instead, if I put it in a glass of water, you will see that the salt will eventually dissolve. Now what is dissolution? Dissolution is it will eventually break into Na plus and Cl minus, so it will dissolve. So these are, you can say, the chemical properties of the salt and the pen I am talking about. Now we have another property which is called the magnetic property. So to understand this, you can have a simple analogy. If you bring a magnet and you bring it very close to this pen, you are right that the pen will not attract to the magnet because this is not a magnetic in nature. Now supposingly if I have an iron pen, so iron pen will definitely attract to the magnet because of its properties. Now the point that I am making is that all the materials have its specific properties, and to measure these properties of the materials, the measuring of these properties of the material is called characterization. So we need a tool called characterization to measure all the different properties of the materials. Now in this lecture we will be specifically focusing on the optical properties. Now amongst all the mechanical, chemical, thermal, electrical and the optical properties, in this lecture we will be talking about the optical properties, and specifically in that we need something which is called spectroscopy. Now we will be studying about the spectroscopy in our next slide. So yes. So coming to the very basics, now what is spectroscopy? Now before even talking about spectroscopy, let's talk about very basics of EM waves. Now EM waves are the energy that travels in the form of electrical and magnetic field in our universe. So this is very elementary, you must have studied this in your primary class maybe, but let's talk about this because we will be talking about the EM waves in detail, and also I will be repeating this the terms of EM waves very frequently, so it's important to learn about them. So let's talk about the EM wave. So if this is the direction in which our electromagnetic wave is moving, so we have the two components in EM waves. First one is the electric field, the other one is called the magnetic field, which I will represent as M, or you can also represent as B. So these are the two components of the electromagnetic field, the electromagnetic waves, and we see that they are perpendicular to each other and they are also perpendicular to the direction of the motion of the EM wave. So these are the two components of electromagnetic waves, and also I will be talking about some of the basic terms. So let's talk about some of the basic terms like wavelength. So our EM waves follows a sinusoidal pattern. So we have something which is called crest and we have something which is called trough. So the above region is called crest and the below region is called the trough. And also the basic terms which is very frequently used are called wavelength, frequencies and energy. Energy is the energy of the wave by which it travels. The wavelength we talk about is the distance between two consecutive troughs, or you can talk about two consecutive crest, or you can talk about this distance. So this distance here from one particular crest to one particular trough is called the wavelength, and it is represented by lambda. And also there is a term which is called frequency. Now frequency can be understood by the number of oscillations this electromagnetic wave is having in a particular second. So we have here a basic formula which is E is equal to h nu, or we have a relation in which E is equal to hc by lambda. So here E is our energy of the EM waves, the mu here is the frequency, and the lambda here is the wavelength of the EM waves, and our h is our Planck's constant. So there is a relation, and according to it, if we increase the energy, our wavelength, our frequency is directly proportional to frequency would also increase, but our wavelength is inversely proportional. So you are right, the wavelength will decrease. So based on the wavelength and the frequency, we have divided the electromagnetic spectrum into various kinds of you can say about various kinds of waves depending on the wavelength and the frequency. So we have something which is called radio waves, we have something which is called microwaves, we have the infrared waves, we have the visible region, we have the ultraviolet, we have the X-rays, and we have the gamma rays. So these are all classified based on the wavelength and the frequency. So let's first, before moving to the technical part, let's first talk about the very basic applications of these waves. You must have heard about some of these waves in your practical application. So, let us talk about the practical applicability of all the segments of the EM waves and how we are using it in our daily lives. So, we have the radio waves. So, the radio waves, we are extensively using these in our daily telecommunication networks. So, these are usually used for the communication devices. We have the microwaves. So, we all in today's world we all have microwaves at home. So, we heat our food with the help of microwaves. So, microwaves we are using daily to heat our food. And then we have infrared rays. So, infrared rays are used in our daily remotes. So, the remotes that we have for the electronic devices to change the channel, or the AC remotes, TV remotes, any remotes that you have has the infrared sensor on top of that. And then we go to the visible region. This visible region is the only region of the electromagnetic spectrum that we could visually see. And so, this is the part of the electromagnetic spectrum. It is called infrared because it is just beyond the red region, that is why it is called infrared here. And we have the ultraviolet because it is just beyond the violet color. So, we call it ultraviolet. So, coming to the next, we have the ultraviolet. So, ultraviolet is usually used for sterilization. So, it kills the bacteria in some form of sterilization processes. In industries it is used. So, it is one of the examples. And then we have X-rays. If you are lucky, you might not have faced X-rays, but whenever you face an accident or something, usually doctor prescribes X-rays to image your bones. So, X-rays are used for that. And then we have gamma rays. So, gamma rays are very high energy in nature. It is usually used in the nuclear physics or for the reactions and everything. So, what we see from here, that when we go from the radio waves towards the gamma rays, our energy is increasing. So, from left to right the energy is increasing. So, according to this relation, you can pause the video and think about what will happen to the frequencies and the wavelength I am talking about. So, just refer to this relation and think whether if the energy is increasing from radio waves to gamma rays, what will happen to the wavelengths or the frequency. So, yes, you are probably right. I have also written here. So, if the energy is low, so here for the radio waves the energy is low. So, our wavelengths is high. So, here if we see the wavelength I am talking about, lambda here. So, the wavelength here is larger, and if you see wavelength of the gamma rays, it is very less. So, the order I am talking about is the wavelengths is about 10 to the power 3 meters and to the order of 10 to the power of minus 12. So, this much difference is there when we go from the radio to the gamma rays. And similarly, if you talk about the frequency, frequency is directly proportional. So, if energy is low, our frequency is also low. So, the frequency, if you want to compare, so frequency is measured in hertz. So, it is of the order of 10 to the power 4 for the radio waves, and it moves up to the order of 10 to the power of 20 in case of gamma rays. So, this is all the basics of the EM waves and all the classification of those. And after talking about the practical applicability, let us talk about how we can utilize this in our characterization of materials, right. So, we have a table here in which I will draw first, it will be much easier for you. So, the energy is increasing from the microwaves to the gamma rays here. So, let us practically talk about all these waves and how we can use it for the characterization of materials. So, first we have the microwaves. Microwaves is very low in energy, as I already talked about. So, this can usually change the rotation of either the electrons or the nucleus. So, we can use it in electromagnetic resonance or ESR spectroscopy. So, we can have an application in that. It gives us the idea about the rotation of the electrons. Then we have the infrared rays. Infrared rays is slightly more energetic than the microwaves. Now these infrared rays will be absorbed by the molecules present in the your material, and it will cause vibration. Now this absorption will cause vibration, and it will give us the characteristic about information about what all bonds are present in that material. Moving towards the UV visible is slightly higher in energy, so it will cause electronic transitions. So we can measure the electronic transition in detail. I will discuss this in the next lecture. So then we have the X-rays. X-rays we can use, they are higher in energy, so they have the ability to knock the innermost electrons of the atoms. So this can be used for X-ray diffraction and also X-ray fluorescence. So this we will be talking about later. And then we have the gamma rays. So gamma rays are very highly energetic in nature, so we usually don't use it in general characterization. So this is extensively used for nuclear reactions and nuclear physicists. So the takeaway message is that if we talk about the characterization of materials, we extensively use these three regions of the electromagnetic spectrum, where we have the X-rays, UV visible and the infrared rays. And in this lecture we will be talking about the infrared rays and how we can use this, and the practicable applicability of the IR rays for the characterization of materials. Okay, let's talk about the basics of the IR spectroscopy. Now to understand the IR spectroscopy, you have to take an analogy in which you have two ping pong balls and which is attached by a spring. So here you see this figure. So here we have two ping pong balls and this is attached by a spring. So after it is attached by a spring, you can imagine that if we compress or we stress that spring, it will eventually vibrate. So that is the basic. It can either be stressed, it can be compressed, and it will cause some kind of vibrations, right? So this is what the analogy of the principle of the IR spectroscopy. So in which we say that every bond, every molecule is bonded by a spring kind of bonds, and every bond has a natural resonance frequency in which it vibrates. So every molecule has its particular vibration. So depending on the type of bond and the type of molecule, we can have different vibrations in a particular molecule, right? So let's take some of the examples. So here we have the different kind of vibrations that can be present in a molecule. So it can be either symmetric stretching. So either this can be possible, symmetric stretching, in which both these atoms are moving together. We can have an anti-symmetric stretching in which these are moving anti-parallel to each other, so the motion is not together. And then we can have rocking, in which both of the bonds are moving towards the sides. We can have a wagging kind of bonds, in which both the atoms are moving in front, so in front of the screen, if you can see. And then we can have something which is called twisting. Twisting is kind of anti-parallel stretch between the both the molecules in the plane which is coming right forward. Then we can have scissoring. Scissoring can be anti-parallel motion in which both the molecules are moving in the sidewards direction or in the y direction, you can say. So these all kinds of vibrations can be possible in our some molecules, and based on that we have a technique called IR spectroscopy, and it can detect what molecules are present depending on the type of vibration it shows. So coming to the working mechanism. So let's first talk about the instrumentation. So the basic necessity for the IR spectroscopy is the IR source. So we have a IR source, we have a sample which is kept at a distance from the IR source so that it can absorb some of the IR, and then here we have the detector, right. So, we have the IR source. So, IR source incidents some of the IR light onto our sample. So, some of the part is reflected back, which I will represent as R. So, some of the IR rays would be reflected back to the source, and here is our sample. Our sample will absorb some of the IR light, and some of the IR light would also be transmitted. So, whatever light is not absorbed by the sample would be transmitted. So, transmitted is the non-absorbed light from the sample. So, and then the transmitted light reaches our detector. So, what basically we say that this is the very basic plot of the IR spectrum that we get. So, we plot it in percentage transmitted versus the wave number here. So, versus the wave number versus the percentage transmittance. So, the transmittance is 100% here on top and transmittance is 0% below. To understand this in detail, let us take an example of ethanol. So, here we have the ethanol molecules. So, in which we have the carbon-carbon bonds, we have the carbon-oxygen bond, and we have the carbon-hydrogen bonds, and we have the oxygen and hydrogen bonds. So, these all bonds are present in ethanol. So, based on the wavelength of the incident wavelength, all of these bonds will absorb the specific wavelength, and it will cause the natural, which matches with the natural frequency, and it will vibrate. So, depending on the vibration, we can record a spectrum, and we could get the characteristic IR spectra. For example, if we have OH, so the transmittance will absorb start from 100%. So, whenever there is a OH vibration, so we will get a characteristic OH peak. Then coming to the CH vibration, we will get a CH peak. For example, we have at 3000. Then we have another peak here, which is represented by CO. It is around at the 1000 that you can say. So, depending on all every bond, it will absorb a specific wavelength of the IR, and it will cause the natural vibration. It will increase, and we can finally see it in the IR spectrum here. So, this is the characteristic IR spectra of ethanol. And coming to one of the exceptions. So, if we talk about the IR, we can actually identify what all bonds that are present in our material, but it has a limitation. So, in case we have polar bonds, so supposingly we have a carbon dioxide which is represented here. So, we have the carbon, we have the two oxygen bonds are there, which are on the same plane, and depending on that, we could either have a symmetric stretch, we could have bending, we could have a asymmetric stretch. Now, there is a concept that you must have probably studied in your +2, which is based on polarity. Now, based on the electronegativity of every material like oxygen and carbon, because they are different. So, because of their difference in electronegativity, they can have a partial polarity, partial positive and partial negative, which is delta positive and delta negative charges creation. So, as we have the vibration, we have the creation of delta positive and delta negative charge for some time, and depending on that, we have polar bonds and the non-polar bonds. So, what the point that I am trying to make is the polar bonds that we have is IR inactive. So, supposingly if we have the CO2, we have the asymmetric stretch and we have the symmetric stretch. Now, in case of asymmetric one, we have a partial creation of polarity. So, this would be IR active, and it gives a bond at around 2349 centimeter inverse, which is the wave number, while if we have the symmetric stretching like this, it will be IR inactive. So, wherever we have the symmetric stretching or symmetric kind of vibrations, that would be IR inactive, while the asymmetric stretching or all the asymmetric vibrations would be IR active. So, taking this into mind, we get the IR spectrum and we analyze it. We analyze the IR spectrum taking the polarity into consideration. So coming to the applicability part, so we let's take one more example before that. So let's take an example of toluene here. So we have a toluene. So this is the structure of toluene. We have carbons and hydrogens, and we have the cyclic chain. So you could see that it is plotted in percentage transmitted, and it starts from almost 100. So you could see that there are several peaks representing several different kind of bonds in toluene. So you could see that we have a peak around 3600, so 3060, I beg your pardon. So that's for the CH stretching, and the peak at 2925 also represent the CH stretching, and we have also CH stretching for at around 3033, but the aromatic and alkyl stretching are different, so we can differentiate between them. Also our carbon and hydrogen shows two different peaks. So either they have, as I talked about earlier, it can either show stretching or it can even show the bending kind of vibrations. So we have both stretching peaks and bending peaks. They are different. We can differentiate them in case of carbon hydrogen CH bond. And similarly we have the CC bonds and we have the CH bending groups, which is differently represented here. So what I am trying to make that even if the carbon and hydrogen are same, we can distinguish between the aromatics or the alkyl CH, or we can differentiate between different types of vibrations between them, the CH stretching or the CH bending, or these all kind of based on the vibrations that are present. Now let's talk about the applications. Now the first application that comes to your mind is the identification of the unknown material. So supposingly you have an unknown material, like you are archaeologist and you get an unknown sample and you want to see what all material or what all bonds are present in case of that material. Now the advantage of FTIR is that FTIR is non-destructive technique. That means your sample is not being depleted in any kind of analysis. It's very easy to use. You can directly use it, and also it could be used in solid, in thin films, or even in liquid modes in some of the models of the IR spectroscopy. So we can use it to identify the unknown bonds that are present in the materials. So if you have the unknown sample, archaeology sample, and you simply run it through IR, so you will get a IR spectrum. So something like this you will get, and then you match all the peaks with the literature available. So every bond will have the specific absorbance in the IR region, and based on that we have a literature present. So we have the standards literature which is present, so we can actually match them with the standard, and we can find about what all unknown components are present inside our sample. And then another application that it can be used is, so supposingly a person is a synthesis scientist. So supposingly he is a chemist or he is a material scientist, and he has synthesized several kind of materials. So supposingly he has synthesized ZNO, I would talk about. So supposingly he has synthesized these ZNO particles, and he want to see whether the material has been successfully synthesized or not. So what he will do is that he will quickly run it through the FTIR, and the FTIR will have the characteristic Zn and oxygen peak somewhere, and that will eventually confirm whether our Zn and oxygen is present in this sample or not. And he could say that after he sees there is a peak of Zn and oxygen, he could say that my ZNO material has been successfully synthesized. Now these are also used to study the chemical reactions, and also in some case whether some of the dyes or some of the materials has been absorbed on the surface or not. So supposingly we talk about an example in which ZNO is used for this ZNO particle that you have synthesized is used for some reactions in which there are some dye molecules or some drug molecules that are eventually attached on the surface. So, you have the ZNO molecule and there are some drug molecules that I am saying. So, these are attached on to top of that. So, we do a functionalization reaction and we attach the drug molecules on top of the zinc oxide particles. So, we want to see whether our drug molecule has been successfully attached to our surface or not. To know that, we will run it through IR. So, we will have the FTIR, the IR spectroscopy of ZNO alone, then we will have of the drug alone, and then we would have what we see the IR spectroscopy of ZNO and drug together. So, drug will have some of its characteristic peak, our ZNO will have the characteristic peak, and if all those peaks are present in our sample in which ZNO and drug are attached, we could successfully say that our drug has been attached onto the surface. So, this could be extensively used for the biomedical field and also by the chemistry scientists, the chemical people, the archaeology people, and also this confirmation of the drug molecule or any other molecule on the surface could be done by the help of the IR spectroscopy. Also, coming to the electronic applications, so you have your MEMS devices and which has several steps of the metal deposition or deposition steps in which you deposit either the thin films or you clean the surface regularly. So, you can use the first very basically you can use it to identify the impurities in your samples. So, supposingly you have a silica wafer and you do an RCA cleaning. So, you quickly run it through the FTIR or the IR spectroscopy to see whether our impurities, all the impurities has been removed or not, and if IR detects any peaks, that means apart from silicon, if it detects any other peak, that means some of the impurities are present on the samples and more cleaning is required. So, detection of impurities can be done for the electronic devices, and after every stage of the thin film deposition or in which we have multiple layer growth, in which we deposit different thin films, different metal deposition is taking place. So, after every step we can run it through the FTIR and we could see whether our metal is being deposited or if we are depositing some other oxide layer or some any other layer, whether it is successfully being deposited or not, we can analyze using the FTIR spectroscopy. So, it can be extensively used for the MEMS device or device fabrication also to analyze each steps. So, after talking about the application, I will summarize what we talked about today. So, in summary, we basically talked about the basic properties of material. So, what are the basic properties of material, like the optical, magnetic, the thermal, and all the different properties we studied in very basic details, and then we talked about why we need characterization and why it is so important. Then we talked about basics of the electromagnetic waves and their divisions or the different electromagnetic waves based on their different wavelengths and the frequencies that are present. Also, we talked about some of the practical applicability where we are using these EM waves in our day-to-day lives, and also how they can be used for the characterization. Then we talked about the spectroscopy and the basics of the IR spectroscopy and how the basic working principle of that, some of the basic instrumentation parts, and then we saw the working mechanism, and also we talked about some of the example of ethanol and the toluene and the carbon dioxide, how some of the vibrations are IR active and some of the vibrations are IR inactive. So, we talked about that also. Then we talked about the practically applicability of the IR spectroscopy in the biomedical field, in the archaeology field, and also in terms of the material and the chemistry. And also finally, we talked about how we can use it in the electronics device fabrication also. So, our FTIR in summary is very useful technique. It is non-destructive and you could use it extensively for various kind of applications. So, that is all for today. Thank you very much, and we will be talking about the UV visible spectroscopy in our next class. Thank you very much.